Today, I'm going to be talking about last-mile logistics, otherwise known as the multi-vehicle routing problem. This is one of the most difficult problems in an emerging battlefield. The number of different types of resources, say drones or trucks, the number of different types of things that you would need to deploy, say food or water or ammunition, each of these adds to the complexity of this problem. I also want to mention that today I'm going to be running this entire demo on our Leap production system. Everything I'm going to be showing today is being run in the cloud on Leap in our online integrated developer environment. So this is all available now. So let's go ahead and talk about the problem. Say that I have a single central depot with a collection of supplies. And then I have a set of forces that need to receive supplies. So say there's a force over here that needs 100 units of water, 100 units of food, and 100 units of other supplies. And there's a force down here that needs 200 units of water, and 100 units of food, and 200 units of other supplies. I have 2 drones to do it, and I'd like to deliver this as cheaply as possible. And for now, I'm going to define cheaply as being the shortest distance. So let's go ahead and run this. And when we do, what we'll see is that each of our two drones goes on a route that passes the sniff test. This was just run on our hybrid system that makes use of the quantum computer, so it's always good when the basic test does the thing you expect it to, which is to go to the different locations. But drones are in some case a best case scenario, so let's make this a bit more complicated. Instead of using drones, let's use trucks. You'll notice that here we are using the actual street plan of Rockhampton. These are an actual location, with actual streets, and I want to take a moment to just dwell on this because at D-Wave, we pride ourselves on being the practical quantum computing company, and we really mean it. We really like working with real data, and that's part of the reason that we've centered this on an actual city, so that we can be using actual street plans. So we're going to use trucks, so they have to follow streets, and instead of having 10 forces, let's have 70. And instead of having 2 vehicles, let's have, say, 7. Let's go ahead and give this a run. So, as I mentioned, in this case, while I'm running this, it is going to be submitting a job to one of our hybrid solvers. These hybrid solvers combine the best of classical and quantum resources together so that they can give you the power of quantum, but the scale of classical. You're getting the best of both worlds. And that's what's allowing us to solve these problems of up to 70 different forces and up to, say, 7 different trucks. In fact, we can solve much larger problems, but I wanted to be able to do it on a demo here for you all today. And using the power of quantum and classical, we're able to really access this sort of full-scale problem. So once again, you can see the different trucks and the different routes that they've selected. I can sort of zoom in, and I can see that this green truck went on a different path. They do nice things like they say follow one-way streets, which maybe isn't so relevant in the context of a battlefield, but say in a context of emergency preparedness or some sort of crisis situation, whether that's a hurricane or a tornado or something like that, being able to follow the street plans is probably important. It even goes around traffic circles. If I zoom all the way in, you can see, oops, that's a lot of zooming, you can see that it passes around traffic circles. We can also see how far each of the individual trucks went. So, vehicle 1 went 2.5 kilometers, and vehicle 2 went 3.5 kilometers, and overall they went about 22 kilometers total. I also want to take a moment to mention that here we're using distance as our metric, but we could actually encode much more complicated things into this type of problem. You could also we just are defining a cost between each of the individual forces locations. You could imagine encoding other things, like the amount of rubble on the street, or the amount of danger that the truck might experience, or maybe the weather. All of these different factors and constraints can be put into this formulation very easily, which makes it a very powerful and flexible formulation. Okay, so I've shown now solving this on our hybrid systems, but let's go ahead for completeness' sake, compare this to classical. So I'm going to run the same problem on a classical algorithm called k-means clustering. K-means clustering is one of several state-of-the-art algorithms that solves these sort of problems. it's a good benchmark. It's one of many that you can do, and it's a good sort of sanity check on what we're able to solve. And if you go ahead and look, you can see again, it solved the problem pretty adequately. It's passed the sniff test. None of these routes look particularly strange. But when we scroll down, what we see is instead of going 22 kilometers, we've actually required 30 kilometers of truck distance. And it's always nice when that works out in a live demo, so that's good. So I hope you've walked away with the understanding that we can be accessing this problem with hybrid, getting real results on a real scale today. So thanks all. Appreciate your time.